For coming to the fall 2016 faculty lecture series. This is Meredith Anderson, and she got her degree at New Mexico State down in Las Cruces a little over a year ago. You've been up at Adams State for about 2 years, right?
A little over a year.
A little over a year.
Second year.
Okay, second year. And she's going to talk about life in two-dimensional space, which sort of confuses me, but go right at it. So you have about an hour, and so maybe some time towards the end for questions. I'm sure there's going to be lots of questions.
Let's hope so. Well, thank you so much. So I'm Meredith Anderson. I'm going to be talking today about, my talk is called A Brief Tour of Flatland. So we're going to be talking about what life might be like in two-dimensional space. So I want to thank everybody for taking the time to come out here tonight. I know that some of you may be baseball fans, so I appreciate if you're missing the 7th game of the World Series to be here. So I'm from Cleveland, so it is a little bit rough for me, but I will still enjoy the time here. So just a little outline on the talk. Maybe some of you have heard the term flatland before, maybe you have not. So we're going to talk a little bit about what flatland is and the origins of the term. Then we're going to spend some time talking about what life is like in 2 dimensions and some interesting problems that maybe crop up in a 2-dimensional world that we do not face here in 3 dimensions. And then we're going to talk about how a creature living in flatland could figure out maybe the shape of the world that they live in. And then last, we're going to talk about why this conversation is relevant to us non-flatlanders. So what is flatland? Well, it's a land that is flat, right? So what you should imagine is just a 2-dimensional world that is completely flat. So maybe I could think about this screen as being flatland, or maybe the surface of the whiteboard back here as being flatland. This is just a 2-dimensional world. The creatures that live in flatland are, of course, 2-dimensional objects, right? So maybe I could have various shapes moving around in flatland. And so if this is my picture of flatland, I've got maybe 4 creatures living here. These are all various shapes, and they're allowed to move around in the north-south direction as well as the east-west direction, but they can't come out of the board. They can't go behind the screen either. So a common misconception about flatland is that maybe oftentimes people think of these creatures as sort of living on top of the 2-dimensional surface, right? So maybe if I were thinking about this desk as being flatland, and I've got my 2-dimensional circle here, right? So if this were my 2-dimensional world and this is my creature in it, he's not on top of flatland. He's actually inside the surface of the table here, right? And of course, in flatland, there is no height, right? So there is no 3rd dimension, no height. So the table here, the surface has no thickness whatsoever. So these creatures are actually moving around inside of the surface as opposed to on top of it, right? Okay, so this term was introduced by this man. His name is Edwin Abbott. And no, that is not a typo. He does have 2 Abbott last names. That is because his parents happened to be first cousins, which is not something that was entirely uncommon at the time. So he was born in 1838. He went to school in England, and he studied theology as well as mathematics. And when he graduated, he became a priest for a little while, but then he decided to give that up because he wanted to get married to someone other than his cousin. So he got married in the 1860s and became a school teacher. He was a headmaster of a school in London, and he worked there for about 25 years, and in that time, he started to write. So in 1889, he decided to retire from teaching so he could focus more of his time on writing. Most of his works were theological works, but he also wrote quite a bit about mathematics as well. And his most famous work is a book titled Flatland, A Romance in Many Dimensions. So this book was written in 1884. It's a novella. And Edwin Abbott published this book under the pseudonym of A Square. So A Square, there he is right here. He's the main character, he's the protagonist, and the book is really an autobiographical account of his life in 2 dimensions. So the book talks a lot about some interesting things that happen in 2 dimensions, as well as some of A Square's thoughts about life in other dimensions. So I would categorize this really as science fiction, or maybe more appropriately mathematical fiction, but it also served as a social commentary on life in Victorian England at that time. So all of the characters in Flatland were obviously various 2-dimensional shapes, and in particular they were all regular polygons. So a square is an example of a regular polygon, and what we mean by that is that all of the angles are the same and all of the side lengths have the same measure. So, you know, other creatures that lived in Flatland, there were equilateral triangles, squares, pentagons, hexagons, heptagons, and so on. And the nobility were those creatures that had more sides. So the more sides a regular polygon had, the higher up they were. Women actually in Flatland were 1-dimensional creatures, so that added another interesting element. So it's a very interesting read. At the end of the book, A Square is visited by a 3-dimensional figure, and he is sort of enlightened as to life in higher dimensions. So if you're interested, it's a very good read. It's a quick read, and at the end of the talk, I will give you information about where you can find that book. So that's the origins of the name. So now we're going to talk a little bit about what life is actually like in 2 dimensions. All right, so here is a picture of 2 flatland creatures. We've got a square and we've got a circle. So the first question I want to think about is, what does the square see when they look at the circle, right? So as everyone here looking at this screen, we're looking at it from a perspective that the square does not have in 2 dimensions, right? We're looking at this sort of from outside of Flatland, right? So we have this additional perspective where we can see both the square and the circle, and we can see all of them, right? We can see their outsides, we can see their insides. But if we want to try to think about what the square sees when he looks at the circle, right, we need to try to put ourselves into life in 2 dimensions. Yeah, exactly what Marty's doing, right? So if this is our 2-dimensional circle, right, you're looking at it from the front, whereas the square is looking at it from the side. So if we want to see what they see, we need to sort of imagine ourselves in Flatland. And what do we see? We see a line, right? We see a line. So from the square's perspective, the circle just looks like a line. And of course, the length of the line segment is just the width, right, of the image that he sees. All right, so here's another Flatland guy. Suppose we've got a square now looking at a diamond. So depending on the position of the diamond, right, the square is definitely going to see a line segment, but the length of that line segment is going to change depending on the position of the diamond, right? So in the top picture, he's looking at the long side, so he sees a longer line segment, whereas when he's looking at the shorter side of the diamond, the line segment he sees is shorter. And so this may seem a little bit strange to us, but actually the way that we see things in 3 dimensions is analogous to this. When I look out at the room, I'm not actually seeing 3-dimensional objects. I'm seeing a 2-dimensional image, but my brain takes, you know, the light in the room along with the perspective I have and my brain converts it into 3-dimensional images. Just like when I watch TV, right? The TV screen is 2-dimensional, but my brain fills in the gaps and I imagine it as being 3-dimensional. So the same thing is happening here. When the square is looking at his 2-dimensional friend, he's really seeing something that's 1-dimensional. But perhaps the lighting in Flatland and his perspective helps him fill in the gaps in what he can see. He imagines to be a 2-dimensional thing. All right. So any two-dimensional creature, when they're looking out on the world, they see something that is one-dimensional. All right, so here's the last case. So a line segment could exist in 2 dimensions. So what's the square going to see this time? They just see a dot, right? Okay, so they just see a dot because the line is perfectly behind its front point, right? Much like if I'm caught in a traffic jam, sometimes I can only see the car right in front of me because the cars in front of them are perfectly lined up so I can't see them, right? But, you know, if the road curves, then I could end up seeing more of the line segment. Okay, so this is sort of what happens, what the two-dimensional creatures see. So now let's talk about some interesting problems that a flatlander might have. So what is different about life in 2 dimensions than life in 3? So the short answer is really everything is different. Everything is different. I'm going to provide you with some examples of things that I find to be very interesting that are different about life in 2 dimensions, and maybe we can at the end sort of talk about some more. Okay, first of all, a figure can't sit down or jump. Right, I'm sort of cheating here because when we talk about jumping, I'm sort of moving into the 3rd dimension. So I can't jump up because there is no up. Okay. Second, knots can't be tied in 2 dimensions. Right, so if, you know, so for instance, if a flatlander had a pair of shoes, they couldn't actually tie their laces. Right, so the reason why is if I'm trying to tie a knot in 2 dimensions, I would end up having to cross one lace over the other, right? But I can't move anything over anything. Over doesn't exist. So if I wanted, are there markers in here? Well, oh, yes. So if I wanted to make a knot, right, if I wanted to cross this over the other one, right, it would just end up breaking this into 2 pieces. Okay, so we can't tie a knot. Nails cannot be used. So oftentimes we use nails to sort of join 2 things together, right? If I wanted to nail a roof on a house, for instance, right? So maybe this is my sidewall and maybe this is my roof. If I wanted to use a nail to sort of merge these 2 things together, right, it would just break the roof into 2 pieces. Right, so if I tried to put it in here, it would just break the roof into 2 pieces. So I can't use a nail to join objects. Their digestive systems would have to be different. Right? So we know in 3 dimensions, the way our digestive system works, right? I eat something, some stuff happens on the inside, right? And then eventually it comes out on the other end, right? So if we had a 2-dimensional creature, I'll draw a triangle because I'm not very good at drawing. So if we had our 2-dimensional creature here and maybe a 2-dimensional slice of pizza, so if he decides to eat this piece of pizza, and if he had a digestive system that were similar to what we have, right, that would be some hole going from his mouth to the other side of his body, right? What I notice is that this would cut him in half. So if he were to eat in Flatland, he would have to come up with some adaptation so that, you know, he could actually eat without being cut into 2 pieces. So that's something interesting. All right, they'd have a hard time making maps. Now you may say to yourself, what, a map is 2-dimensional? Or at least if I'm imagining the paper as having no thickness, it's 2-dimensional, right? I mean, I could draw a map like this. Maybe this is some flatland town, some other flatland town. And then if I drew my flatland creature, right, and he wanted to look at this map, the problem is he can't see anything. All he can see is the outline of the map, right? So he can't see anything that's happening inside of the map. So maybe we could change things by just saying, okay, the map has no edges and we're just going to make this a maybe 2-dimensional model. He can just move his way around, right? Just like we make 3D models of certain things. But he'd have to actually be able to sort of move around in there to get anything useful out of that map. Their artwork would be much different. When you think about two-dimensional artwork, well, again, you might say, well, I can make a painting. That's two-dimensional, right? If the paint has no thickness on the piece of paper, that's two-dimensional, right? Well, so I get the same problem as what we had with the map. So if I make a painting, maybe I'm going to draw, let's draw the Mona Lisa. So, you can see why I'm in math and not art, right? So if I drew the Mona Lisa, we have the same problem with this creature who wants to look at this artwork. All he can see is the frame that this thing is in. Even if we erase the boundaries here, right, he can still just see the outlines of her face. So, when we think about making art, a painting or something like that, we see it as a two-dimensional, right? We're in 3 dimensions, but we can think about art, a picture, as being two-dimensional in many cases. So maybe the analog for a two-dimensional creature, when we think about artwork, maybe it would have to be one-dimensional, right? So maybe their artwork is, some sort of line. Maybe I've got different colors on that line, something like that. Okay, so there are many other things that we could talk about how things might be different in Flatland. Here's another interesting question. What if they built a road? All right, so here I've got a picture of life in Flatland. I've got a road, I've got 3 creatures, a triangle, a hexagon, and a line segment. Right, so if I look at this hexagon here, right, he can just see this side of the road and this green line segment. He can't see his triangle friend that's on the other side of the road. Similarly, this triangle, when he's looking in the right direction, all he can see is this line which represents the left side of the road. He can't see his friends on the other side. So if we had a road in Flatland, then the road would just cut Flatland up into pieces. Right? So nothing can cross it, which means we can't have any chicken crossing the road jokes. I love corny puns, by the way, in case you didn't notice. All right, so here's one more problem for Flatlanders. Suppose I've got 3 houses in Flatland and 3 utilities that the Flatlanders want to connect up to. So maybe we've got water, gas, and sewage. We've got 3 Flatlanders, and they would really love to have all 3 of these utilities. So if we wanted them to have all 3 utilities, then each of those houses would need to have a wire connecting the 3 houses to each of the 3 utilities. Okay? So maybe to start out with, we'll just take house 1 and we'll connect it to these 3 utilities here. Now we need to connect 2 up, so maybe we can connect 2 this way to the water and then to the gas and then to the sewage. So now house 3, right, we can connect 3 to the sewage, no problem, right? But the problem comes when we want to connect 3 to the water, right? What happens is, if we were trying to connect the 3rd house to the water, it would end up having, that wire would have to cross over one of the wires that already exists, right? And we know there is no over in Flatland, so that would just mean that we're breaking the wire into 2 pieces, right? So now, obviously, I chose these connections on purpose, right? And you could try to connect these up in a different way to see if maybe it would work. But it turns out that this is something that you cannot do in just 2 dimensions. If we have 3 houses and 3 utilities, we cannot physically connect the 3 houses to the 3 utilities without one line crossing over another. So this is called the utility problem. And so, if we think about this in terms of our world, if you're thinking about your house and your 2 neighbors' houses and you have utilities, 3 utilities to connect up to, then that means that it's guaranteed that there will be one wire at least that crosses over another wire. Right? So, we're going to move on and talk a little bit about shapes of Flatland, but there are many, many other interesting questions that we can ask about life in 2 dimensions, and I really encourage you to do that, and I'd be happy to talk with anybody about some other fun things that they think about in life in 2 dimensions after the talk. Okay, so the next question that we want to answer is, what are the possible shapes of flatland? What are the possible shapes? So probably when you start thinking about flatland, you think about it as just a flat surface that has an edge to it. Right, so if I think about that whiteboard over there, I could think about that as being my two-dimensional world, and it has edges to it, right? And so, if we had a flat surface with an edge, there's the question of could, if we moved up to the edge, could the figure on it fall off, right? At one point, we used to think about the Earth as being flat with maybe it had an edge, maybe it didn't, So could flatland be flat with an edge? Another possible shape is that it could be a flat surface that extends infinitely far in both directions. So in mathematics, we call that a plane, right? So it extends infinitely far in both directions. A third possibility is maybe it's the surface of a sphere, like the Earth. And you may say to yourself, hey, that doesn't seem two-dimensional, right? If I show you a sphere, right, if we think about the surface of this sphere here, this doesn't look two-dimensional, right? Right? So the idea is if I think about trying to move myself into flatland, right? So if I could imagine maybe melting myself onto the floor so that I am in flatland and I have no height, right? So the Earth is so big that I can't tell that it's not flat from here, right? If I go out into the middle of the desert in the San Luis Valley, right, the Earth looks pretty flat there, I'd say. Right? So maybe we could put flatland in quotations, right? It's not, there is some curvature there, right? But when, if I'm looking at a close scale, it still looks pretty flat. If we look at it from very, very far away, then we can see that it's actually curved, but up very, very close, it really does look flat. Okay? So the surface of a sphere is actually two-dimensional. If I think about the whole sphere filled in, that's certainly three-dimensional, but the surface is just two. Okay? So maybe flatland is like the surface of a sphere. Okay? And then are there other possibilities? Are there other two-dimensional worlds that could exist? And the question that we really want to answer is, if I were a figure that lives in flatland, if I'm a two-dimensional creature living in a two-dimensional world, how could I figure out the shape of the world that I live in? So this is the question we really want to figure out. How could we figure out the shape of the world that we live in? So certainly if you were a flatlander living on a flat surface that has an edge, that way we could find out. Right? You could just try to walk in one direction and see if you come to an edge, and then hope you don't fall off. Right? Theoretically, we could also figure out if it's a flat surface that extends infinitely far in all directions. Of course, we would need an infinite amount of time to do that, right? But if I could move on forever, the idea is I could figure out if it extends infinitely far in all directions. But how could a flatlander figure out, for instance, if the world they lived in is the surface of a sphere? Okay? So to try to answer this question, we're going to talk a little bit about some properties of spheres for a moment. Okay, so let's think about how we determined in 3 dimensions that our Earth was round, right? So we've known for a very, very long time that the Earth is not flat, but that we actually live on a sphere. And the way that we determined that the Earth was round is that we can see it, right? If you hike Mount Blanca, you hike to the top, you can actually see the curvature of the Earth, right? If you're sailing out in the ocean and you see a ship out on the horizon, you can physically see it dip below the horizon, which means you can see the curvature of the Earth. If you're traveling in an airplane, you can also see the curvature of the Earth, right? So we've known for a long time that the Earth was round, right? But all of these observations are using our special perspective, right? Our 3-dimensional perspective. Because if I'm on top of Mount Blanca, right, I can see out into, the air above the surface of the Earth and see that it curves. So I'm using my special perspective of height to figure out that the Earth is round, right? But a 2-dimensional creature living on the surface of the Earth, they don't have that perspective, They don't have that perspective. So how could a flatlander figure this out? All right, so something else that happens on a sphere is if I start at any point on the sphere and I walk in a perfectly straight line, eventually I'll get back to where I started, right? Now this, of course, is assuming that I can walk over mountains and I can walk through oceans and over buildings and that sort of thing. But theoretically, if I stand here and walk in a perfectly straight line in any direction, I'll eventually get back to where I started, right? So one of these lines, if you took a path like this around the Earth, the path that it would trace out is a circle, and that's called a great circle. So a great circle on the Earth is one that cuts the Earth into two equal pieces, right? So if I lived in Flatland, right, this would be something that I could actually test. If I lived in Flatland, so if I melt myself onto the floor, and so I move in one direction in a perfectly straight line, I should be able to get back to where I started. And this doesn't use anything about the perspective of the third dimension. So this is something that a flatlander could check. All right, so I'm about to tell you guys a true story of a flatland creature who was interested in learning the shape of the world he lived in, okay? So this creature, this is a flatland bug, and they've studied a lot about different dimensional spaces and mathematics, and they wanted to figure out whether or not their world was round, okay? So they wanted to see if their world was round. So what they decided to do is they decided to take off walking around their planet, and they wanted to see whether or not they would get back to where they started. Okay, so this bug sets off heading north, and she decides to trail a string behind her because, okay, I want to make sure that if I get to the ends of the Earth, I don't fall off, so I'm going to trail a string behind me. And she finds out that after she walks for a while, she ends up getting back to where she started, but she's coming from the south direction. So she says, that's awesome. This must mean that I am on a sphere, right? So flatland must be spherical. So this would be the path that the bug takes. They start here, move north, and then walk around the back of the sphere and end up coming back to where they started. So she says, hey, I must be living on a sphere, right? But she's a scientist, and she's like, okay, I should test this a little bit more before I'm 100% certain that I live on a sphere, because there could be some issues here. So a potential problem to her claim that her world was a sphere is, maybe she was walking in a path that's not actually a straight line, and maybe she ended up just tracing out a large circle. Right? So it turns out, us three-dimensional humans, we're really bad at walking in straight lines. Right? Mythbusters confirm this, so it must be true. Okay, so we're really terrible at walking in straight lines. We tend to favor one leg over the other. And if we try to walk in a straight line, we tend to walk in a circle. The same is true for flatlanders. So they tend to favor one side over another. So she says, okay, maybe I ended up just tracing out a large circle. Maybe I'm not on a sphere. So she says, I'm going to try again. But this time I'm going to move in a separate direction. So she takes off traveling east, and she walks for a while, and she comes back in the west. She says, hey, that's awesome. I made sure I walked in a perfectly straight line. I walked in one direction. I got back to where I started. Right? So I must be on a sphere. Then she's thinking about it, and she realizes that on her trip, she didn't encounter the wire that she had laid out on the first try. Okay? So if we try to think, if Flatland were a sphere, and we took two different paths around the sphere, so this was her first path. She walked north around Flatland, came back up from the south. Then on her second trip, she went east and came back from the west. If Flatland were a sphere, then that means that she should have encountered the first wire she left in the backside of the sphere, because we know any two great circles on a sphere have to intersect. Right? And she would know if she hit her other wire, because she would have had to physically break it into two pieces to move through it, right? So she says, hey, maybe this isn't, maybe this flatland is not actually a sphere. So she gets a little frustrated and burnt out and decides to take her dog for a walk. Okay, so she takes her dog out on the dog's one-dimensional leash, and the dog takes off ahead of her. He starts running ahead of her. In a few minutes, he reappears, but from the other side. Okay, so what happens is the dog takes off in this direction and comes back from this side. So she gets an idea and decides to try to pull on the leash to see what happens. This is a true story. I'm not making this up, okay? This is true. She decides to try to pull on the leash and see what happens. And the leash gets caught on something, okay? So let's think about what would happen on a sphere. So if this is the path that the dog takes on a sphere and this is the leash, right? So if we're on a sphere, if she pulls on the leash on the sphere, then she'll always be able to pull this thing in, assuming that there's nothing in the way. So assuming maybe it can go over mountains and over buildings and that sort of thing. She'd always be able to pull the leash in because as she pulls it, it would slide down the sides of the sphere and she'd eventually be able to pull it back into her, right? So you can also see why she has so much time to think about life in several dimensions because she lives by herself on her own planet. So anyway, this is a theoretical experiment. So okay, so she cannot possibly be on a sphere because if she were, she'd be able to pull the leash back into her. So let's look a little bit more about the path that the dog takes. So this is the path of the dog. It takes off in this direction and comes back from the south. So somehow the north side of Flatland is connected to the south side of Flatland. So the dog traces out a circle that looks like this, right? So it traces out a circle that looks like this. So somehow Flatland must curve around on itself. Maybe I could imagine it as being a cylinder, something like this. Okay, so maybe Flatland is a cylinder. And if Flatland were a cylinder, so this is just the surface of this paper towel roll, right? The center here, this hole in the center does not exist, right? That's not part of the universe. And so if they were trying to pull on this leash, right, it would get stuck around the hole in this cylinder and she wouldn't be able to bring it back to her, right? Without tearing the universe, right? She'd have to tear open the cylinder to be able to do it. So she says, hey, maybe Flatland must be a cylinder, okay? So she wants to see if the same thing happens when she moves in the east-west direction. So what she does is she takes another walk, and now she goes east, and she's trailing a rope behind her. And when she comes back to the same spot from the west, she again tries to pull on the leash and see what happens. And what happens is that, again, it gets stuck on something, right? So, all right, so she's already figured out that Flatland must be like a cylinder. But now if I walk in the east direction, I come back from the west. So it must be that the east and west side of Flatland are also joined up, right? So Flatland must look like this. Yeah? Have any of you guys seen this before? Looks like a donut, right? So in this case, Flatland is like a donut. Right, of course, here we're not talking about a three-dimensional donut, not a filled-in donut, but really just the surface of the donut, so maybe like an inner tube, right? And so we can see the two paths on here, right? This is the first path of the dog, right? And she was not able to pull in the leash in this direction because it gets stuck around the inner tube, right? Whereas if she's moving in this direction, when she tries to pull the leash in, it gets stuck around this hole in the center, right? Okay, so this in mathematics, we call this shape a torus. Right? You may say to yourself, oh, I've never seen this before. I can't imagine this actually being a universe in any sense. But I claim that you may be more familiar with a torus than you think you are. Does anybody recognize this? So this is the Asteroids game. This game came out in, I don't know, the late 70s, so a little bit before my time. But this was an arcade game where, so the object of the game, you're this ship in the center, and the object of the game is to blast apart asteroids, right? So these asteroids are sort of moving around in this universe, and you're supposed to break them apart. Well, this universe is really interesting. It has interesting properties that you may or may not have seen before, right? But when these asteroids leave the side of the screen, so if this asteroid leaves the right-hand side, it always comes out on the left. Right? And if this one leaves through the bottom, it comes out on the top. You guys noticed that before? So somehow in this universe, the right side of the universe is connected to the left side, and the top is connected to the bottom. Right? So this is an example of a two-dimensional universe that is a torus. Right? So if I were to join up the left and the right side, and then the top and the bottom, I would end up getting a donut. Right? Okay, so back to Flatland. So not all of Flatland has been charted, right? And there could be some weird behavior that happens in other regions, right? She's already found one hole in this thing, right? But maybe there's another hole somewhere else in Flatland. Maybe there's another 10 holes somewhere else in Flatland. Yeah. Did you have a question? Yeah, she would. She may have to travel a little bit further, right? But maybe she could do the same sort of thing, right, to try to find out if there is a second hole. Yeah. So there could be other possible shapes, other possible two-dimensional worlds that could represent Flatland. So now the last part of talk is really sort of how do we make this relevant? Why is this question, why is this discussion really important for us non-Flatlanders? Well, so if we're looking at these two possible Flatland worlds, right, we can tell the difference between these easily because we have this extra perspective where we can actually look at them from outside and see different properties of them, right? I mean, this is, you know, a donut versus a donut hole. I can see the difference, but if I live inside of Flatland, it's much harder to tell these things apart, right? So the way that we told these things apart is, well, if I think about there being maybe a rubber band or something around this sphere, right, I could always pull it in without it getting stuck on anything. Whereas if we had a rubber band around this torus, for instance, right, I cannot actually pull this, right? I can't actually pull this around without breaking the rubber band because it gets caught around this hole here. And this is something that a creature living inside of Flatland could figure out. So how is this related to questions from our world? So one of the main questions of interest in some areas of science is trying to figure out the shape of the universe. And maybe you've never thought about the universe as having a shape. Maybe in your mind the universe is just some flat thing that extends forever in all directions, or maybe it ends somewhere. Is there an end to the universe, right? But, you know, there was once upon a time where we thought that the Earth was flat, right? We thought that the Earth was flat. And, you know, we ended up learning that that's not actually the case. And one of the reasons why this is really important to know is because, well, one, it's interesting. And two is, if I wanted to try to navigate around space, it would be very useful for me to know what the shape of the thing that I'm navigating in is. right? For instance, we learned a lot about navigation on the Earth by learning that it's a sphere. You know, if I take an airplane, the path that an airplane takes is along one of those great circles that we talked about earlier. In navigation, if I'm sailing a ship, right, we always travel along arcs of great circles. So if we want any hope of being able to move around through our universe and navigate properly, we should know what the shape of the universe is. But the problem is we're stuck inside of the universe, right? And it's really hard to be able to figure out the shape of something when you're stuck inside of it, much like this two-dimensional creature that was trying to figure out the shape of his world. One of the active areas of science research now is trying to answer these questions. Can we use techniques that are very similar to the techniques that this two-dimensional creature used? Can we use these techniques to figure out the shape of the universe that we live in? So this is some information about the books that I referenced. So Flatland you can find easily on the internet if you just Google that. And here are two other books that are very interesting reads if you like the idea of learning more about life in two dimensions. That's it. Any questions? Yeah.
Very briefly the social hierarchy of different shapes.
Yeah.
and I happened to open the book and read one page a little earlier today.
Oh, okay.
And it talked about the fact that shapes that don't have equal sides are of a lower class because they don't have equal sides. They tend to be soldiers or workmen, and the more sides that they have, then they're of the higher classes. If you get to the circle, and that struck me as very much a commentary on social life in England at the time that he wrote it.
Yeah, very much so. And as I had mentioned, the women are one-dimensional, and that he gets a lot of mileage out of those jokes in that book, and that's also part of it too. I don't claim that he actually thinks that women are of lower dimension than men, but yeah, it is very much so. It's an interesting read. And some of the figures that are born, if they're not perfect regular polygons, then some of them are destroyed at birth. So it's serious business in Flatland. Yeah.
How many sides does a circle have?
Well, I mean, I guess in one sense you could think about it as an infinite-sided polygon. Yeah, so the more sides that a regular polygon has, the more it looks like a circle, right? So in that sense, as the number of sides increases, it becomes more circular. So you could think about a circle as having infinitely many sides. Yeah. I would think that would be the top. Yeah, so with every generation, the children that are born, they have one more side than their parents do. Yeah, so when the square has a kid, it's a pentagon. So, unless something goes wrong. Yeah. Yeah, Marty. Right, so, well, I don't know the answer to that. It's certainly a harder question. I mean, it's not like we can send a ship out trailing, a rope behind. But the ideas, the mathematical ideas are still the same, right? If I can theoretically take a rope and sort of catch it around a hole, then I notice something about the shape. As far as the tools go, this is a problem that they're working on, but we certainly don't have fine enough tools to really say what the shape of the universe is yet. As far as whether that will happen in the future, I certainly hope so. When that would be, I don't know. But they're definitely working on exploring these techniques.
I'm trying to think, there was shadows in Flatland.
This is something I was thinking about a lot this morning, actually. So it's sort of, it depends on where the sun is, right? So if the sun is inside of Flatland, there would be a lot of shadow, right? If you had any, if I had the sun in any building, everything behind it would be in shadow. But if you're thinking, if the sun is maybe outside of Flatland, then maybe you couldn't escape the sun. Yeah, so it really depends on where the light is coming from, which, it depends on the perspective that you have of a Flatland universe. Yeah.
I'm having a hard time thinking of Flatland as having an edge, because when I think of an edge, I think of depth. So I must not be understanding Flatland right.
So it would be, if we're thinking about this as a three-dimensional universe here, then my edge would be one of these walls, which is two-dimensional. So if we're thinking about the same thing in Flatland, they're living in 2 dimensions, so an edge would be something one-dimensional. So it would be like a line, if I'm thinking about if I'm bowling, for instance, and I have my bumpers up, right? If I'm, if the ball hits one of the bumpers, that's like an edge of Flatland. I'm just imagining it being a line instead of having several dimensions to it. Does that help? Yeah.
So if you drew out like an equilateral triangle, 2 dimensions, and put a bigger one and then a bigger one, would the change in the angles of the government or the torus or sphere or
So if we have equilateral triangles, right, the angles then are the same.
well, on a sphere they're not, they're a little bit less.
Right, okay, so
And what would they be on a torus?
that's a good question. So it would certainly, the triangle would have a measure that would be greater than 180 degrees, the angles, because it has the same positive curvature that a sphere does. I'm not exactly sure. I'd have to think about that a little bit more. I'm not exactly sure on what the angle would be, but there would be a similar phenomenon. Yeah.
That's sort of how people have tried to answer that question. I mean, there was a mathematician named Gauss that tried to measure a triangle between mountain tops and see if there was any curvature that deviated from flat space, but it was, it was not within experimental error to tell the difference between them.
Right,
So
we
still
need a much larger triangle. Right?
Just the word torus was new to me. How do you spell that for the donut shape?
Torus. Yeah. Mm-hmm. Yeah, Frank.
So in Flatland, the adjustment system be an actual?
I mean, I think that there are several different possibilities. I mean, maybe, so we've got our, our intestines sort of, not up in some sense. So maybe if they had a digestive system that makes sort of like a puzzle piece fashion, maybe, they could end up still moving around and not being cut into 2 pieces. Yeah, yeah. I mean, that could certainly work. That might introduce other problems. Yeah, I think so, right? Yeah. 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 They'd be in the pizza. They'd be in the pizza. Yeah. Yeah, so topping would not be the appropriate word. Inning? Yeah, I don't know. Yeah.
When you showed the line, it was a circle. A circle is round, and when you showed us looking at it, it had it was two-dimensional, but from the square's perspective, when we were looking at it, it was circle, which means that the sides would go out.
Yeah, that is a very, very good point. That is a wonderful point, right? So when we're looking at the front of the line, all we can really see is just one single point, whereas what we actually saw, you're right, was a circle. And the problem is that it's, we can't actually draw something that doesn't have any dimension to it on a computer. That is a wonderful, wonderful comment, yeah. Yeah, so it would be it'd be infinitely thin. Mm-hmm. Yeah. Well, and that was one of the concerns about women in the Flatland book, since they were one-dimensional, right? Is if they're coming straight at you, you can't see them, so they could theoretically pierce you and just break you into pieces. So. It's a really good read. It's really interesting. Any other questions? Thank you. That was a really fun question and answer period.